Hi there, so today we're going to be recreating this sparkly Blender shader that I made. There are a lot of really cool techniques and there's a lot to learn. So, for anyone who's seen my old stylized Galaxy shader tutorial, I made that back when I didn't have a mic and it's sort of more fast-paced. A lot of people struggled to follow it, and instead of recreating a newer tutorial, I decided to recreate this more recent shader I made that uses a lot of the same techniques and some new techniques. I know it's been a while, videos aren't exactly my forte, but I wanted to try making a tutorial for this, so yeah. First of all, I will be using the Blender NPR branch, but most of this is possible without the NPR branch, and I will get into alternatives for things. For example, the main thing here is the repeat zone in shaders. If you're not using a Blender version with the repeat zone, here's the alternative way that you would go about using iterative processes in a Blender shader. So, the way the repeat zone works is it takes this vector here, and it adds this value right here to it. And then it plugs it into the output, and in a later iteration, this output will just go back into here, and we will add to it again. So if you set this to one iteration, it is essentially the same as what this node group is doing. This vector here is the same as this here, and on the inside of this node group we're just adding 1, 2, 3, here we're adding 1, 2, 3. Now, if I were to set this to, say, 2 iterations, this is the equivalent of taking 2 of these node groups and pairing them like this to each other. If I set it to 4 iterations, it is the same as taking 4 node groups like this. As we get into very high iteration counts, like say 64 iterations, you can imagine how this is just a much cleaner way to represent these iterative processes, and it's also much more computationally friendly, it's much faster. So the first thing we're actually going to do is set up a ray marcher. What ray marching is, for those who don't know, is it's a 3D rendering algorithm. It's a way that you can render various 3D volumes, sign distance fields. It's a very versatile tool. We're going to be using it to render the sort of like fractured geometry inside of Suzanne. Now, the way ray marching works is actually pretty straightforward. Let's say we have a sphere like this, and our camera is over here. If a ray is going in this direction, then instead of trying to calculate the way a ray at this origin going in this direction would intersect with the sphere using all kinds of complicated math, we are instead just going to start at this position and sample our 3D sphere some distance away. We're going to move some distance, and this is going to be called the step size. If we don't see our sphere, we simply try again, and we keep moving forward like this until we hit our sphere. Now, this approach obviously has some drawbacks. In a situation like this, it is very possible for a ray to overshoot, where we check right here if we hit a cube, and we check right here to see if we hit a cube, and oh no, we didn't hit a cube, even though this ray clearly should register as hitting a cube. So a solution for this is if we had some kind of formula that could tell us the distance to our scene at any given point. This is what an SDF does. Let's add a square down here just to demonstrate this more. We are going to check the distance to the scene at this starting point, and we know that we can safely march out in any direction by this distance without overshooting anything. So we march out in this direction based on the distance to our scene at that point. We can then check the distance at this new point and repeat our process. As we get closer and closer to the sphere, the distance to our scene gets smaller and smaller until at some small threshold we say, yeah, we hit our scene. So, because this is an iterative process, I'm going to first add a repeat zone here. I'm going to add a position here, and this will just sort of be the position of our ray. It'll be the ray origin as it progressively moves further and further away from our camera. So I will name this RO for ray origin. Now, we can actually get the position of Blender's camera using the vector transform node. You want to set this vector to be 0 all around, and set this from camera to world. Now, Blender also gives us access to its own ray direction that its camera uses via this incoming ray. This incoming ray actually represents the direction of rays entering the camera, So we are going to invert this by multiplying it by -1, just like that. And this is our ray direction. Now we need to make a sign distance function. The simplest one we can make is a sphere, and this right here is how we get the distance to a sphere of a given radius. I will call this SDF. So now what we want to do is, from this ray origin, we want to sample the distance through a scene. We want to then scale our ray direction by this distance, and add that to our ray origin, like this. If we then plug that into here, we can now preview this little scene right here. It doesn't look like a sphere, but if we increase the number of iterations, you can see that our sphere will take shape. The coolest part about this is that SDFs are incredibly versatile in how you can render them with ray marching. For example, if we plug a fraction in right here and make our spheres a bit smaller, we can now render an infinite grid of spheres. Ray marching is pretty cool. Now, in order to get the fractured shape that I had on my shader, I used Voronoi. By using Voronoi, we can again render an infinite grid of spheres, this time with random positions. Because Voronoi is ultimately just returning the distance to a whole bunch of points, so by subtracting from this, we can make that the distance to a whole bunch of spheres instead. Instead of f1 Voronoi, however, we want to change this to distance to edge. This is going to look very strange because we are now using the edges as our distance function. So we want to invert this, and the way you can invert this is by moving this to the bottom of the subtract node like this. By changing the scale now, you can see that we can render these individual sort of fractured Voronoi cells. By the way, in case you see any kinds of artifacts with your Voronoi like this, the reason for that is because the distance is not correct. When you scale your Voronoi like this, the distance also scales with it, which means if you set your Voronoi scale to 5, you will be marching 5 times further than you should be. A very simple fix for this is to set the scale to 1. Let's say you still want to be able to customize the scale of your Voronoi. Well, this is easy. You simply need to divide the Voronoi by whatever value you're scaling it by. If you're making it 5 times the size, you need to divide the final distance by 5. All of our cells have disappeared, and that's because they are so small that this 0.3 value that we're using here has stopped representing them. By lowering this value, you can begin to see all these cells again. Now, we have a bit of an issue here. The cells themselves are actually rendering on top of the mesh. There's a really cool and intuitive solution to fix this. Let's say this is our mesh right here, and this is our camera again. It's sending a ray this way. Instead of starting at the camera, we can simply start at the mesh's position right here and ray march still using the same camera ray that we were using before. This will ensure that no objects in front of the mesh will be rendered on top of it because the ray is starting from the mesh's surface rather than from the camera's position. Luckily, our position vector is right here, so we can just go ahead and slot that into our ray origin here. And now you can see that our cells are rendering on the inside of our mesh without rendering on top of it. Now we're going to tweak the scale of this Voronoi. You can use the subtract node here to change the scale of the cracks, and I think for now I will probably leave this at 1, maybe 0.75. I want larger fragmented cracks rather than a bunch of tiny shards. But of course this all comes down to artistic preference and the look that you're trying to go for, so definitely use these techniques and experiment. Use different distance textures if you want. My old Galaxy shader actually used noise textures for this, and it had a very different style. If you're satisfied with how your Voronoi looks, you can add Refraction now. Luckily, Blender has a very cool Refract vector math option right here. Now, you want to plug the ray direction into the top and the normal into the bottom. There's a small issue with our Refraction, where the IOR here is actually inverted from what we would expect. I don't know if this is a bug or not, I haven't actually looked too much into it, but it's an easy fix. You simply have to use division to take the inverse of the IOR you want to use. If we want an IOR of 1.5, you just plug in 1 divided by 1.5. If we then look at our ray marching again, we need to replace this incoming ray direction with the refracted ray direction by plugging it into here. And now you can see that we have this glass-like refraction on our surface. The coolest part about this is that it's even completely physically accurate to how ray-traced glass would refract things on its interior, because we are directly influencing the ray directions of our 3D rendering, which is very cool. Just to make this a bit more readable, I'm going to add a reroute here, and I'm going to rename it to RD for ray direction. Now, while we're returning a position vector for our cells, the position vector for where the SDF actually intersects with the surface of our mesh is obviously incorrect. It again looks like it is rendering sort of in front of our model here. The reason for that is because our SDF stands for signed distance function. The interior distance of our Voronoi is negative, which means even though our rays should exclusively be marching from the surface of the mesh inwards, the ones that are intersecting with our cells actually march backwards and see the backside of our cells. There are a couple ways we can fix this. One approach is to clamp this value here. I'm going to use a different method because this approach is actually going to help us out with normals later. Add a mix node at the end of our ray marching here, and duplicate our SDF node. Instead of using it in our ray march, we simply want to look at it by itself using this position vector here for our mesh. We want to check where the SDF is less than 0 because that will highlight where the interiors of our cells are like this. If we plug this into the factor for our mix node, we can see that we have properly masked out where the cells intersect with Suzanne. By plugging our position vector into here, we now have an accurate position vector that we can use for anything. Speaking of normals, we might as well get those right now. The way you get normals in a ray marcher is pretty straightforward actually. We can approximate them with the SDF itself. If you've taken pre-calculus, you might know that you can approximate the derivative of a function by sampling two nearby points, and the height difference between these 2 points represents how steep the function is at a given range. We need to do this in 3 dimensions. This will essentially try to look at values in our SDF and try to estimate which direction they're pointing, going from lower values to larger values. And this intuitively makes sense. As you move away from the surface of a mesh, the SDF obviously increases. If you're moving parallel to it, it doesn't change at all. And that change is something that we can approximate the same way you did in pre-calc. Now that I've cleaned stuff up, I'm going to duplicate the SDF node here, and we're going to plug in our position vector, and it should generally look black. This makes sense because we are trying to represent the surface of our SDF, and the distance to the surface at the surface is obviously 0. Where the values are greater than 0 actually gives us an estimation of the error of our ray marching, where we haven't quite reached the distance of our mesh. What we really want to do is sample our SDF with multiple offsets to try to estimate the normals. I'm going to duplicate it 3 more times so we have 4 of them here, and I'm going to subtract small values from each axis. On the x we will subtract 0.0001 for example. Let's make that a bit bigger just so you can still see it. Here we'll subtract it on the y, and here we'll subtract it on the z. We want to combine these SDFs with a combine xyz node like this, by then taking our unoffset SDF up here and subtracting this with a vector subtract node. We get something that looks almost entirely black. The reason it looks black is because the values we're getting are actually very, very, very small, so we need to normalize them. Luckily, we can just use the normalized node like this, because our normals should have a length of 1 regardless, and we end up with something like this. Now, this doesn't look quite right, and we're actually running into similar issues before, where the SDF intersects with our mesh, the normals are actually incorrect, and we would want to use our mesh normals instead. To fix this, we can use the exact same factor over here, and plug in our regular mesh normals just like this. And now we have our calculated ray-marched normals. I'm going to start putting things in frames just for organization. And now with all of the ray marching stuff out of the way, we can start to get to the fun effects. Let's start by taking our ray marched position again and plugging it into a distance node. Let's then plug in our original mesh's position vector here that doesn't use ray marching, and we get this almost foggy kind of look. This makes sense because where the cells are closer to the surface of Suzanne, the distance should be 0, and where our ray marched position gets further from the original position, it's going to get brighter. Let's then plug this into a color ramp, and you can set this to whatever colors you want. I personally chose pink because I think it looks pretty. Now, you may notice that I've moved these 2 sliders right here very close to each other. This creates a much harder line between the faces of the cells that intersect with Suzanne in the interior sections. This is definitely a preference thing, but personally I like the clarity that it gives. Now that we're focusing on making our shader look pretty, I'm going to turn the refraction back on as well. The next thing I want to do is add some fake iridescence. I'm going to add a layer weight node here, set to facing, and I'm going to use our custom ray merged normals for it. I'm going to plug this into a map range and remap these values to be from 350 to 750. These might seem like strange values, but the reason we picked these is because we're going to be using the wavelength node. This takes wavelengths of light in nanometers and converts it into a color. For example, if I replace this with our window coordinates here like this, you can see a rainbow here. You can use a color ramp if you want, but I really like how this looks, so this is what I went with. Now, let's say you want to add some variation to this. You can use a power node after the facing to change the sort of fall off right here. And we can even use other textures to influence this fall off, such as Voronoi like this. This can give us a much more fragmented look, and you can add a lot of really cool details this way. For example, if we duplicate our Voronoi texture and set this to Minkowski distance, we can create these really pretty star-like patterns. I'm going to set the scale to 15 and tweak this less than node. I am also going to multiply this by the color here so the stars have random values. By taking the Voronoi that we are currently using to influence the power and subtracting from it by these stars, we end up with a pattern like this. And if we plug this into our power right here, our iridescence has all of these very pretty shiny stars. We can take this a step further by adding even more variation with another Voronoi node. I'm going to set this back to Euclidean distance and change the detail to say 4. I'm going to click normalize so it's between 0 and 1 generally. I'm going to then multiply this by a small value so its influence is very small, and add that to our stars right here. When we subtract that from our final Voronoi, you can see that it adds a lot more details here, and when we plug that into our wavelength, it adds a lot of nice variation, I think. Just for comparison, here's what the iridescence looks like with and without this power node. To combine this onto our base color, you can do this however you'd like. I used the add blending mode, and I think it looks pretty nice. In order to further accentuate the shape of the base mesh that we're using, I'm going to use a layer weight node without our custom normals, and I'm going to plug this into a regular power like this, so I can control the fall off more. I'm going to add another mix node here, also set to add, and I'm going to use this layer weight to add a bluish color, I think. And here it is before and after. I think this really helps bring some of the details back from our Suzanne model. Another way that we can bring detail back is with ambient occlusion. I'm going to add an ambient occlusion node, invert it so that the light parts are dark and the dark parts are light, and duplicate our mix node here. I'm going to set the blending mode to multiply, and I can use this to pick whatever color I'd like for the ambient occlusion. I might go with something purple or bluish. And once again, here's the before and after. One last effect I'd like to add is a sort of glittery effect. Let's start by using this Voronoi so I can explain how it works. By subtracting 0.5 from the RGB, we can make it so that this Voronoi color is between negative 0.5 and 0.5. We can then normalize it to make a bunch of random vectors out of this. By then getting the dot product between this vector and our incoming ray, we create an effect where the Voronoi cells fade in and out depending on the viewing angle. Because these values are between negative 1 and 1, I'm going to multiply add to map these back to a 0 to 1 range, just like this. And from here I can add a power node, which I can use to control the falloff. If I set this to something like 10, for example, it is mostly dark with these brighter glints compared to before where it looked like this. I can then add another mix node up here and use this to add on various colors that we get from our Voronoi texture here. This adds a nice bit of color variation, but let's say I want it to conform to our ray merged geometry instead. I can simply use our position vector that we got up here and plug it into the Voronoi, and now our iridescence and everything will conform to it. By changing which normals we use, either our ray merged ones or our base normals, and same with our position, our ray merged position or our base position vector, we can control whether these effects conform to the ray merged geometry or the surface of Suzanne, which gives us a lot of fine-tuned control. Lastly, let's duplicate this glitter setup here and use another Voronoi texture. this time set to a much smaller scale, something like 100. To make it look more like isolated glints, you can increase this power node here to something that you're satisfied with. I'll go with 200. I'll then use this to add another bluish color on top of Suzanne. As you can see, a lot of these effects are being combined onto our final color just using add or multiply with a color mix node. It offers a lot of artistic control, and there's a lot of room to experiment, so honestly just have fun with it and make cool shit. Like, my compositing setup is fairly minimal. I simply use a color balance here to bump up some of the colors. I push the pinks a bit more with the gamma, and I push the greens a bit more with the gain. The greens really contrast the magenta, so that's just what I've chosen to accentuate. And here you can see before and after. You can add bloom, vignette, various effects. I also really like to use a box sharpen, because I find that it really makes it pop a lot more. You obviously want to tone down the strength of this so it's not as extreme. I set it to something like 0.4 or so. Lastly, in my original shader, there was a cool edge highlight effector on the top and bottom of the model. This is actually done using the new NPR nodes. You can go over to the output, add a new NPR tree like this, and up at the top, you switch from object to NPR. Using the image sample node, you can offset how you sample the screen texture. By sampling the combined color, you can offset it in screen space like this. By sampling the position vector instead, you can use this to extract an edge highlight. You can go about this in many ways, but the way I personally went about it is by transforming this vector from world space to camera space, separating the z values, and then subtracting the original position vector that has no offset at all. You can then threshold this value to control how sensitive geometry is to outlines. And you can change the offset to control how thick the outline is. You can then use the combined color and these masks to add various outline effects, like a bright blue rim up here, or a purple outline at the bottom. I hope this ended up looking similar to the original. I think it's pretty close, but I will show the original again here. Regardless, I think it looks pretty, and it covers all of the techniques that I used in the original fairly closely. Obviously, I spent a lot more time tweaking colors and getting things right, and there's a lot of room for just artistic expression here, so have fun with it. But yeah, it's been a while since I've made a tutorial or a video at all. I don't really do these kinds of things. I find it difficult to motivate myself to make things like this, but if you'd like to see more of this and support me, I'll have a Ko-fi link in the description. I don't think I'm going to set up a Patreon because I don't trust myself to upload consistently, and I think receiving consistent payment would make me feel really bad, but any support is appreciated, and it would be nice to know if people want to see more videos like this. I could probably make more videos like this in the future, but no promises because tutorials aren't really my thing. Still, I hope you enjoyed, and thank you so much for watching.